Good morning. This is the third part of our series on operating system, Forgate, which can also be used for regular coursework. In this, we are again going to visit on process state or state transition diagram. In case if you didn't understand in the previous video, or you can say that I might have gone too quick or hastily over the topic, so I'm again going to explain this, though I have kept that part in my video. So, process diagram differs for different type of operating system. For uniprogrammed operating system, there are only four states, namely the new state, the new state, the running state, when the process is in execution, or the next state is the block state required during IO operation, and termination state when required for completion. So when, as you have already know that in uniprogrammed operating system, uh, only one process is to be present in a memory. So as soon as that process is created, as soon as that process is created, it is directly moved to the running process. So when the process is running or executing on CPU, it can do two things. It can either it either make an IO request, which takes it to the block state, or it can complete its execution and move to termination. Yeah. While a process is in running state or block state, the process resides in main memory. While if a process is in new state or termination state, it resides in secondary storage. So, if the process is in block state, then it has to go back to the running state to finally terminate. A process cannot terminate from a block state. Therefore, after IO completion, it goes back to the running state, after which it again has two options for completion or again make an IO request. Okay. Similarly, for multi-program operating system, there are five state instead of four, like in uni-programmed operating system. Uh, these five states are new, as we have as when a process is created, a ready state is added in multi-programmed operating system. As you are aware, in multi-programmed operating system, there are more than one process to be present in the main memory. So a ready state is to be needed to contain all that process that are present in a memory and that can execute. Running is the same process in execution completed. That state is defined by a terminated state. Block state is same as when a process needs an IO operation or makes a system call. So yeah, goes over to the state. When a process is created, it moves from new state to ready state. Now if we have only one processor in our system, then only one process can be in the running state. So therefore number of process in the running state is one, and only one process can be scheduled or dispatched to the running state, while ready state can contain more than one process. If a process is in running state, it again have two path. If it's got completed, then it can go to terminate state, or can sorry, it has three paths. One is for the completed state. Second path is that of if needs IO operation or system call. Then it goes to the block state. As you are aware, we have already studied that multi-programmed operating system in preemptive scheduling. A process can also be preempted because of time and priority. So a process can go back to running state, go back from running state to ready state if it get preempted due to time and priority. And a process in block state can go to back to ready state after completing IO operation or serving the interrupt, or serving the system calls. It is point to be remember here that in multi-program operating system, when a process moves from block state, uh, after IO completion, it goes to ready state, not the running state. A process can only go to running state from the ready state. Okay, so in multi-programmed operating system, if a process has to be executed in a CPU, it has to be moved from running state it has to be moved from running state to it has to be moved from ready state to the running state. Yep, sorry. Yep, yeah. So a process in ready, running, or a block state is always resides in main memory, while a process is in new state or terminated state. And now what we are also gonna see, a suspended state resides in secondary memory. So if the previous diagram is clear, see, if a process is to be scheduled and is present in the main memory, and what happen is that the resources required for execution is not available, then process, what happened to the process, then process is suspended and goes to the suspended ready, which means that in suspended ready means that a process want to execute, but there are not enough resource available for execution. And if resources become available again, then that same process goes back to ready state via means the process can resume its execution if it is allocated to the CPU. Now, from the block state, uh, if a process is in block state, which means it is waiting for an IO operation, block state waiting for an IO operation or a system call. If while waiting for an IO operation, what if the resources it was allocated? Uh, what if while during IO operation it required resources that are currently not available? Means the resources required is not available, means it does not have resources to continue its execution. Then it can again also can suspend it, and then it moves to suspended block, and then from suspended block it goes to resume, means to complete IO operation there are sufficient resources are not available. Okay, after IO completion it can goes back to the ready state, which is like similar in the previous diagram. Yeah. And also a process might get suspended, but it is very rare to be get suspended from the running state to the suspend ready state. It is very rare, but sometimes in some books it is written. Resource preemption, yeah. The other thing is that while a process is in ready state and some resources get preempted, then it can move back to the block state. So basic, you just need to understand is that for the suspend ready state means that it doesn't have any resources to complete its execution, and it is moved back to the suspend ready state. And for the suspend block state, resources are not available to complete even its IO operations. Therefore, it moves to the suspend block state. Both when a process is in suspend ready state or is in suspend block state, it resides in the secondary memory, not in the main memory. So again, for just for the clarification, when the process is in new state, suspend ready state, suspend block state, or terminated state, it resides in the secondary memory. And for a process to be presented to be present in main memory, the state can only be ready, running, and block. Now, this another the next topic here is yep, a scheduling queue. Uh, Scheduling queue implementation. Yep, queues, number of queues, um, processes in memory, CPU, disk process, implementation of process state and queue. Okay, there are basically two queues in general. Uh, there can also be a suspended queue, but we mainly states queue in terms of when a process is in memory. So for ready queue, list of PCB of ready process, and block queue means list of PCB of block process. And that queue is present in form of linked list of PCB. Every device has its own queue. Yeah. If a process is in ready queue, this is just a general diagram. If a process is in ready queue, mean there are five processes, and P3 wants to is currently executing is executing in CPU, but it get preempted, goes to the device preempted for IO operation, and it is goes for the device queue. After completion, this thing moves back to the ready queue. And while a process is in uh, ready queue, It also resides in the main memory. See, even when the process is not in the ready queue, is in the device queue, which means it is working for IO operation, but it is still resides in the main memory. See, P3 is still present here. So this is scheduling, disk scheduling, or not sorry, job scheduling, or not disk scheduling. Basically, there are three types of scheduler: long-term scheduler, short-term scheduler, and a mid-term scheduler. Long-term scheduler is used when a job is created and is moved to the ready state, which means goes to the ready queue from job queue. Job queue is present uh, in a secondary storage. Job queue is present in secondary storage. A ready queue is present in main memory, and a job that moves from job queue to ready queue is done by long term scheduler, and ready queue to CPU is done by short term scheduler. And if a process is running and gets preempted, that is managed by a mid-term scheduler. Mid-term scheduler's work is to get that process ready again for execution. For example, like P3, just we take our example, like P3 is get preempted. Okay, so when P3 is get preempted, it is the job of midterm scheduler to make it available again for the short term scheduler to choose it again for execution. So this is a straight queuing diagram, and there are other queue for IO wait queue, which does like device queue. IO queue can be like, there can be multiple IO queue depending upon the multiple IO devices. For example, every device, as you have already know, that every device maintain its own queue. So therefore, like a printer can maintain its own queue, a mouse can maintain maybe its own queue, maintain its own queue, camera maintain its own queue for processes. Goes to IO and then against to ready queue. There are only two on disk queue, on disk queue yeah, there are only two on disk queue, which is job queue, which means program to be loaded into the memory, and suspended queue means process that are suspended. Okay, scheduler and dispatcher. Scheduler, we already know three scheduler: short term scheduler, long term scheduler, and mid term scheduler. Okay. Yeah, so scheduler are of three type: short-term scheduler, long-term scheduler, and mid-term scheduler. Now we move on to the context switching. So in context switching, what happen is that, as I've already told, that saving the PCB of currently executing process and loading the PCB from ready queue onto the CPU is known as context switching. So it means that the process that are currently running on the CPU, we save the state of that process and load the PCB of a new process from the ready queue. And dispatcher module, it is a module of process manager, carries out activity of context switching. So dispatcher does the activity of context switching. And the time taken by dispatcher, this question has been asked in the previous gate examination. Time taken by dispatcher is also known as context switching time, dispatch time, or CPU scheduling overhead. Why we are saying it is a CPU scheduling overhead? Because we are saying it is a CPU scheduling overhead uh, because CPU is actually doesn't doing any productive work during switching. So it's basically the overhead of the CPU. That's why we are saying it's a CPU scheduling overhead. So there is this the question, something is like that. Time taken to switch between kernel to user is T1. Kernel mode to user mode is T1, and time taken to switch from process to user process is T2. So which time, T1 or T2 is greater? So we have seen that T2 is obviously more greater than T1. Means, see, when a process move from kernel to user mode, it requires only one context switching, or we can say like a mode shifting basically. But when a process needs to be shift from user to user, first the process moves from user to kernel mode, then back to the user mode. So mode shifting plus time for saving and loading the PCB. Time for saving and loading the PCB is basically context switching time. See, as you can see, while switching from T1, T1 is basically like going from kernel to user mode. And for T2, it's basically you go first to the kernel mode, and then the dispatcher will carries out the activity of context switching. Means it just switch the process. And the last point is important, is that loader always resides in main memory. Loader is a part of a program which loads the module uh, from secondary storage to the main storage. It always resides in the main memory. Yeah, this concludes my first note on operating system. There are, I guess, three or four more notes on operating system, and we will also be covering questions here. So yeah, have a damn good day.